Hello everyone. Let's wait for students to arrive. This is the ninth week. Till students are arriving, let's open the assignments. We shall start. Okay. Till people are coming, let's have some discussion. Let's go through the this week's notes to get a better glimpse of the week. Just to summarize, so typically when we talk about estimators, it is inherent that what we expect out of an estimate is that it should give accurate estimates of any quantity that we are working on. It could be more like, let's say you're working on any random variable which have for example, all clinical trials have those estimates of death probability or lethal dose and all those things. So every time we cannot have an expect sample of everything, but based upon the sample size or based upon the reading that we have, measurements that we have, we can expect some accuracy, and an estimate is a helps us in getting more accurate or unbiased estimates. In plain language, the average of estimates across the record should yield true value. Let's say, so when we are talking this, theta naught is a true value, and expected value or the estimated values are theta cap. The expected of theta cap minus theta naught is delta theta cap, and this should be zero for a accurate and good estimate. For example, an unbiased estimator is like mean, simply mean. You take all the signals, do an average, that's it. It's mean. It's a very good estimator, and two random non-correlated variables have mean as the only, or actually a very good estimator. But we understand it is a lot of times very difficult to get multiple data points at the same time, or let's say we're talking about time series, so spatial or time value, it is very difficult to get exact data. Therefore we have, based upon what is the variance, based upon what is the process, there are several estimators, and variance of an estimator is same as what we call variance normally. The variance expression is important because helps in finding out the error in estimate that could be. What would a confidence level, confidence region, range, and helping in designing the experiment and how many experimental factors are required to be studied. And hmm. Okay, so let's say we have our variance of the mean. So see, estimator will give you a mean. What is the variance in the means that is available? That is what we are calculating, and we find that the variance in the mean is equal to the variance in the, so variance in the data. Variance in the mean is equal to the variance in the data divided by n, or variance in the error divided by n. The variance in the mean is proportional to the variance in data. So let's say you have a data. So if you think intuitively that is your data is very good, then using that as, data as the precursor for the estimate, your estimation for the mean itself will also be good, and your variability or the variance will also be less. But if your data is bad, it is highly vague and have a very large variance, in that case your variability will also increase. Your variance for the mean, you which because this data will become the precursor for estimators, and your variability in the estimation will also increase. But we, as we decrease, as we increase the number of data, we see that your variability in the mean will decrease. That's a very good feature of a estimator. Well, it is not important that always the variability is proportional 1 by n. It will be sometimes 1 by n square also. But it is typically, for example, in normal data, you find that variance of the means is proportional to 1 by n. Let's say we have the variance of the vector of parameters. We have several estimation theory is typically used to find out the parameters. So let's say theta cap is the uh, estimated data. As theta cap is the estimate where theta is the matrix of the parameters. Uh, we have the variance. Sorry, theta cap is the vector of the parameters, and we have the variance covariance matrix of the theta cap, that is v theta cap. If you see the diagonal of this matrix sigma theta cap, parameters can be estimated on the individual basis itself. It is not dependent upon the other parameters. But if you see the other the variables apart from the diagonal, you will find that there is a covariance related of one parameter onto the other parameter. You have sigma theta cap 2 to theta 1. So there is a covariance. But in practice, trace or basically the only diagonals are much more used. And it will be much more easier if you convert this into a canonical form and have the lower matrix and the upper lower triangle of the matrix and upper triangle of the matrix in zeros. There you will find out. So if you, let's say you have this variance data, you convert it into a diagonal matrix. So what you will find out that what are the individual variability that is there. Hello Abhinay, we are actually discussing just uh, what has happened in the week. So let's continue. So variance of the vector of parameters. If you convert this matrix into a diagonal form, you will find the eigenvalues of these. Now the eigenvalues have this property that it will convert the variance of the estimated parameters in such a form that they are independent of each other, and that's a canonical form. Typically, either you use the trace of this matrix or its canonical form, you eventually will end up with the same answer. Just it has to be normalized. In because matrix won't change, the inherent property of the matrix won't change. Only the form that you are seeing will change. Minimum variance unbiased estimator MVUE is an estimator of the parameters theta cap z where minimum variance is available. So we have an estimator. It should be, there are two properties that are basically constraints. C1 and C2 are constraints. First thing, it should be a good estimator. It should be an unbiased estimator. Second thing, it should be the variance should be minimized. So this class of estimators are very good in with respect, but with every good thing there is a bad thing also. It's very difficult to estimate and use this kind of estimators. There are several assumptions that are related with this. Formally, the efficiency of an estimator. So you how do you find out whether it's a good estimator or not, whether this has a least variance or not? What you do is you have, let's say, the theoretical lowest value, you divide by the estimator that you have defined, the variance of the mean, estimated mean, and the theoretical lowest variance among all of them. Let's say you have several data points. Uh, there are some estimates that you have, and there are some theoretical values that you have. You just divide their variances, you will get the efficiency. Coming to Kramer-Rouse inequality, it dictates whether the variance is possible. So, like Carnot, or like let's say any limit that you have in, there are several theories that we have learned in several different aspects of chemical engineering and about of different engineering fields also, that there are some limits that we define. We find out that there is some boundary that we cannot cross, and we try to reach towards that boundary. Similar is Kramer-Rouse inequality also. It tells you what is the maximum efficiency possible, achievable variance. Let's say you have several data points, and he found out using the data points your uh, estimates which come up here. The mean of the estimates is this point. The true value, target value is this theta naught. This has a distance. This distance is because of the biasnesses that is inherent in several estimators, and apart because of the assumptions, and maybe because of data. And by now, I assume that you might have understood that what is the main culprit and a lot of things is unpredictability. The variance, the uncertainty that inherents everything is, which is important, which is good. Otherwise, nothing would happen. But it's there, and we have to use. I mean, we our goal is to minimize that variability, minimize that uncertainty. So the most efficient estimator is what minimizes the variability or variance and is unbiased. So Kramer's this efficient, yeah, once again, where's that inequality? We just talked about Kramer's. No, not this one. So Kramer-Rouse inequality is the one that actually helps in finding out that. It helps in finding out which is a good estimator. It's not possible that one estimator is good for every data and every situation and every process. No. But there are some processes where a certain type of estimator is good, and somewhere other type of estimator. For example, you talk about processes which follow Poisson distribution. There your better estimator is to go with mode. Whereas if it follows normal distribution, your better estimators go with mean. Mode, uh, median, and mean, all three are estimators. There are several more estimators. You can follow RMS also, root mean square. That is also there. But our main focus is towards finding out which is the best estimator for our process, minimizing biasness and uncertainty. Okay, we will continue this, but let's go and discuss the uh, question answers of the week. Let S1 square be the sample variance from a population with variance sigma square, and S2 square be the sample variance from a second independent population with variance sigma square. Both have the same variance. Sample size n1 and n2 respectively. Which of the following is the unbiased estimate of sigma square? For this, you can rely on the Kramer-Rouse inequality to find out this. And we found that this one follows. C follows the Kramer-Rouse inequality, and this is a estimator. Given the data generating process, Vk equals to zero point 0.6 E k minus 1 plus Ek, where Ek follows a normal distribution with 0 as the mean and 1 as the variance, using Monte Carlo simulations and report the mean square error of the unbiased sample variance estimator, sigma square Vv is equal to this. Use R equals to 10 to the power 5 realization with n equals to 100 sample per realization. Round off your answer up to 2 decimals. This you have to do using this R, language R. And you will find out about 5, 0.005, 0.05 is the answer. If the point estimates of mean for a random, okay, just a question. Let's say if n would have decreased, what do you think? What would happen? Obviously, the answer would have increased, the variance would have increased. If the point estimates of mean for a random process xk using two different estimators from an n point dataset are obtained as 1 by n xk summation xk and 1 divided by n minus p xk. If p is more than 0, first estimate an unbiased. So what are the different conditions that are possible? That's what we have to find. So as you can see, yeah, the answer is given that if I first estimate is unbiased for infinite n and asymptotically unbiased, and the second one is also unbiased asymptotically. Obviously, if n increases, your variance will decrease and it will become unbiased. But what about this thing? Second, third, and fourth option. See, we cannot say that it is biased or finite. If let's say your x is actually unbiased, then irrespective if you have n1, n100, or n infinite, it would be unbiased. Your biased uh, estimator, your biased signal can become an unbiased signal when your n tends to infinity, but the reverse is not true. I mean, not reverse, but when you say it's a finite data, it may or may not be a unbiased one. So, second and third, both are wrong, and if, the first one is biased and second, so obviously, fourth one does not make sense. For a strictly stationary random signal xk, following an exponential distribution with PDF fk equals to a lambda e to the power minus lambda xk, choose the right option where I lambda and lambda hat are Fisher's information and estimator of lambda hat respectively. One second. Not lambda hat, lambda. Sorry, not lambda hat. Yeah. In an exponential distribution, your mean is actually one. Your lambda is actually one divided by mean, which is actually opposite of actually reciprocal of Poisson distribution. So this would be an answer. Simply taking a mean and equating to one by this thing, the answer obviously first one is not possible. The third one is also not possible. What we have to check is the other part of the question. Is is it Fisher's information or not? This is very easy. You can just it's already given the notes, so you can see that. The lower bound of the variance of an unbiased estimate of a parameter theta, where S yn comma theta is the score and I theta is the Fisher information. So we have to tell what theta would be. So if I theta is a Fisher information, inverse of that would be theta itself. Theta equals to inverse of Fisher information. This is a typical way of writing the score, so this will be that only. This won't change. So it says that it's simply theta, so there's no other thing related to theta. That is why this we can ignore, and we have to just say inverse of the Fisher information. For a random variable x, mu is the population mean and sigma square is the population variance. X bar is a sample mean of an IID sample of size n. What is the correct statement? So the mean, obviously, the x bar is always mu. Is it true? It's not always true, because if let's say you have let's say you have 10,000 samples and there's 100 samples, it could come from anywhere in the region. When n tends to infinity, then only you can say that x bar is equal to mu. Otherwise, it is not. So B is not the answer. X bar is always distributed normally with mean mu and variance sigma square by n. True. What was the answer? Is it not or something like that? Okay, maybe I have done something wrong here. IID sample. One second. Oh, acha, acha. Sorry, I forgot. IID means independent identical samples. Oh, in that case, yes. This is false. Yes, mean x bar will always be mu. Variance of x bar will also be sigma square by n. And this always converges to a standard normal as intended. That the last part is true always in most cases actually. The heat involved in calorie per gram of a chemical reaction is approximately normal distributed. The mean is thought to be 100 and standard deviation is 2. We want to test hypothesis. Null hypothesis is that the mean is 100, whereas alternative hypothesis that is mean is not 100 for a sample of n equal to 9. If the confidence interval constructed from these n observation is known to be 98.5 to 101.5, there's 1.5 of changes there. Which of the following statement is true? where alpha is probability of type 1 error and beta is a probability of type 2 error. If this is the case, we can actually find out the alpha and alpha comes out to be this. This is true. Similarly, if 103 is the true mean, then beta comes out to be this. All for beta true mean equal to 105, beta comes out to be 0. So after that it becomes 0 itself. But till that 103 it is not 0. Before 105 also is not 0. After 105 it's 0. Which of the following statement about confidence level are true? If we have R finite realization of data and if we constructed 95% of the CLs from each of these realizations, exactly 95% of these RCLs will always contain the true parameter. Sorry, not CLs, CIs, confidence intervals. To construct CI, we need to know the true value of the parameter. That's not true. To construct CI, we not require the true parameter. We require the confidence in that. If the width of the confidence interval always converges to zero asymptotically, that is sample size tends to infinity. No, that's false. When sample size tends to infinity, it may or may not go to zero. It's not always goes to zero. If we have R realizational data and if we construct 95% of class interval from each uh, of these realization, exactly 95% of these realization confidence interval will always contain a true parameter. What's the difference in the first and the fourth? Sorry. Okay, it's for finite here. Right. So no, not for finite. That is only valid for infinite. If you have infinite realizations, that is very large number of realizations, then you are sure that your true parameter will lie in the confidence interval. Well, 95% actually means one sigma difference from the mean. Okay, let x1, x2, xn be the random variables RVs with the PDF given below. Which of the following statements are true? The estimated parameter theta cap is equal to 1 by xn xi minus xi bar whole square. So this is the answer. This is not true. This is not true. This is also false. So one second. Oh, son. Out of these two, this is not true. This is true. Theta. Also, we are talking about alpha. Yeah, alpha is equals to x bar divided by theta cap Okay. Which, if you just open this theta cap, you will get this. You just combine first and third, you will get the fourth one. And consider data in the given data given below. y is given, x is given. Suppose you are given the predicted expression for y as this. Find the least square ls estimate of alpha and round root to closest integer. If you do it for this data, you will come nearly about 1.98, 2.01. It comes near at 2 only. So you can write till 2. So because you have to round it to the closest integer. 2 is the answer. So this is the end of the week assignment. Let's go and see the notes again. If you have any questions, we can wait for a little long and then we will start the notes.
Like, should I put it like, I'm too confused. I figure something out. You just can you like properly write down what changes you think I should be making? Otherwise, I haven't done this before, right? So just I'll do the journal then. Okay. Okay. And keep it. Just send the ones that are not working. उसके बाद भी कोई प्रॉब्लम है उसके भी करने हैं भाई उसकी एटलीस्ट वो तो कर सकता है you're going that's fine that's not a problem but उसके तो we can do now it's fine don't worry dude seriously don't worry I'll take care of it just give me like a detailed write-up of what you want me to do okay I'll split the work yeah. No, if people don't work at the last moment like this, then I have to tell the TA that everybody is not working. Then marks cutting वगैरह होगा. Even Pranav will have to go through it because this is last moment. You can't just do it and like raise your hand कि मैंने तो कर दिया मैंने हो गया. So I'll talk to them. Don't worry, just give me like a proper detailed like कि ये करना है ये करना है. ठीक है? चलो. Don't worry, enjoy. Okay. Okay, no problem. Bye bye. हाँ, I mean depends like regulation. 30.
मतलब रीजन ऑन यूट्यूब तो रिकॉर्डिंग यूट्यूब पे चाहिए वो मुझे okay. Let's begin again. So, as per the properties of estimator, the most efficient estimator uh, is when it is in coherence with the Kramer-Rao inequality, which says the inverse of the Fisher information of the parameters of the variable theta is less or equal to the variance of the estimates. So Kramer-Rao's inequality, CR inequality, gives that lowest variance achievable by any unbiased estimator, and this estimate, though, whatever estimate it could be, if it follows this condition, it is uh, an efficient and unbiased estimator. The reason is that, and this lowest bound exists only because uh, the Syn, comma theta equals the Fisher information multiplied by the theoretical estimate minus the data. If because this bound helps, this equation helps in finding a lower bound, otherwise all other values will have Sn uh, less than equal to your the final RHS. The larger information on theta is given, the lower is the availability, and hence the error in theta cap is also lower, which is very not intuitively also correct. An alternative form of the condition of existence of an efficient estimator can be given from The MVUE that estimates CR bound exists if and only if this condition is followed. I mean, this is independent of theta sufficiency and only depend of the observation y. So theta is the parameters. See, let's say you have this experiment. You take hundreds of, uh, let's say what, data points. You using those data points find out theta number of parameters to that your model fits. Whether these theta parameters are sufficient or not is only tell, uh, because see, you can have infinite amount of parameters, but that might not be correct, because rather than choosing infinite number of parameters, we are best we actually find out the real infinite number of data points and just be experimentalist. Why is this the point of interpretation? But interpretation is required because there are several conditions or regions where we cannot do the experiment, and it's very difficult to go to that precision. Therefore, that is exists, and I theta helps in I theta. What I'm saying, no, the minimization. And when it is this quantity is independent of theta, you find out that this is actually should not be plus. If I'm not wrong, they should be equal to. Fine. Okay, let's continue. Fisher information of the mean itself is n divided by sigma square, is equal to sigma, which in turns will give us the inverse of the means, would give us sigma square by n, which is variance of the means estimates. There are several estimates that have been given, which and their consistency, convergence, and pointwise convergence all have been explained. Uh, wait a second. Now this is upon estimators. Method of moments is one estimator. Least square method is an estimator. Matrix inversion is an estimator. Predictor and residual is an estimator. Pseudo inverse is an estimator. And what are the measures of R square with respect to these estimators is given in this PDF. Heteroscedastic errors is actually telling you. So I'm just explaining the main part of it. So all others is very easy to understand. It's nice, but let me just explain this one. That this errors, when you cannot diagonalize this vector of variance, you find out This uh, variance, when turned into eigenvalue form, will help you find out which variable, which parameter is the most important one, which can change your variance. So that you have to consider as the most pivotal point, which will help you in further calculations. Uh, if you have any questions, you can ask, else we can end the session if required. Let's wait for some more time. If no one come, if then we'll end the session.
Hello, sir.
Yeah.
Sir, I had one doubt.
Mm-hmm. Yes.
Uh, yes, sir. Sir, what is significance of 1 sigma, 2 sigma, and 3 sigma? And also, can you tell more about what is confidence interval?
Okay. See, whenever you have a distribution, we have a mean, and with respect to that mean, we want to find out that uh, whether our data rely is closer to the mean or not. If we go 1 sigma away from the data from the mean, 68% of the data is covered. When we go 2 sigma front from the data, 95% of the data is covered. And when we go 3%, 99.7% of the data is covered. Typically, it is understandable in all experimental research aspects that if we go up to 3 sigma and you have the if 3 sigma is your confidence interval, so this data, though, if you say that your p value, when you calculate using in hypothesis testing, you calculate the p value if it is less than 0.05 in a confidence interval, and that confidence interval is the sigmas that you decide. So let's say if I say from minus, if my 2 sigma is my confidence interval, or it is from minus 2 sigma to 2 sigma, then I'm saying that in that interval, what is the probability that my answer would all or my hypothesis will come true, and you find out the p value. So in all experimental research, if you go in all papers, scientific paper, typically people uses 3 sigma. That is the significance that tells us that 99% of your data is correct. But this is not always true, because in recent experiments, people, based on the complexity and the variability of the data, it could be people try to increase their confidence interval such that you have to go up to 5 sigma also a lot of times, which goes up to 99.999 5% should be the confidence such that your answer is true. And if your p value,
Okay, sir.
oh, you understood that.
Yes.
Okay, if there's no,
Yes, sir. Yes, sir. Thank you.
if there are no more doubts, then we can end the session.
Yes, sir. Thank you.
Okay.